So before we move on any forward, I'd just like to go back to this slide again. So the first cartoon here represents usually phase changes. Phase changes, for example, if you are converting solid water, which is ice, into liquid water. Okay, so when this process happens, liquid water has a lower energy. Okay, there's no intermediate step basically in which between solid and liquid phase transformation. Now compare that to systems in equilibrium, chemical reactions. So this one represents chemical reaction in the sense that when your reactants actually react to produce a product, okay, now some of those products, according to the collision theory, will still react with each other to reform the reactants, and the system reaches equilibrium at which you have a given amount of products and reactants, or well, the ratio of the products and the reactants is constant. Okay, this is what those mean. Now let's jump forward into free energy as work. So the term free and free energy was just not chosen for anything arbitrary, otherwise they could have used another word. But that's basically the amount of available energy to do maximum work that is useful. Okay, we're not really going to work on problems like these, but delta G just represents W, or work. Okay, so for example, if delta G is negative, let's say for example for this formation of water vapor, then this just means that 457 kilojoules per mole of energy is actually required or is available to form water. Now the opposite of that, 457.2 kilojoules, if delta G was positive, will be the amount of energy that should be available in order to reproduce hydrogen and oxygen again. Now, achieving maximum work available from a spontaneous process can only occur in a hypothetical pathway, and any real pathway wastes energy. Now, when I discuss, or what I mean rather by a hypothetical pathway, is a reversible process, meaning if you go from point 1 to point 2 to point 3, then you can go back to point 2 and point 3 from point 2 and point 1 from point 3, and have the states similar as to what you started with. But nothing in life is actually a real process. Most of the processes that we have are actually irreversible in nature. So let's say, for example, let's consider the battery in a car. So in a car's battery, electric current flows through the starter motor of a car, and this current is generated from a chemical change in a battery, this chemical reaction of which we can calculate delta G, and from there we can determine, the available energy to do work, the value for delta G. Now, can we actually use all of this energy to do work? The answer is no, because current flowing through the wire causes frictional heating, and the higher the current is, the greater the amount of heat that will be produced. And this heat produced is actually wasted energy. So in the process of charging and recharging, or discharging rather, and recharging, keep in mind that we have a finite flow of current as the car battery is discharged, and also a finite flow of current as the battery is discharged. And in the case of recharging a battery, more work will always be required to recharge a battery than the battery produces as it discharges. So what this actually means is that even though the battery, which for this case is the system, has returned to its original state, the surroundings have actually not, and as a result the universe is different, and because of this, the process of discharging and charging is actually an irreversible process. That's why there's actually a finite life for batteries, be it in cars or in cell phones. Now, at this point, this actually concludes our introductory discussion on kinetics and thermodynamics. And we're going to end thermodynamics with these laws of thermodynamics called Ginsberg's theorem. I'll let you read this one at your convenience. But basically, this just means that life is difficult. Okay. So having closed the chapter finally on kinetics and thermodynamics, their interplay actually provides us great insight on how we as scientists can control chemical reactions. In particular, if we want example from a reaction which produces two products or more, to have one of the products in greater quantity over the other, then the knowledge of kinetics and thermodynamics will actually provide us a way on how that one can be done. Let's say, for example, this organic reaction in which you have this compound, 1,3-butadiene is actually the name of this compound, butadiene, okay? And you add to it hydrobromic acid. This reaction will actually lead to the formation of two products, okay? It will always lead to the formation of two products. You have 3-bromo-1-butene and 1-bromo-2-butene, the structures of which are actually shown here. But basically, the reaction happens in a sense that first mechanism is you form this positively charged carbocation. Okay, we're not going to discuss this for this class, but basically you'll be seeing that a lot in organic. And then once that carbocation is formed, this bromine can actually go and attack, which is actually the term inorganic, either this carbon and this carbon. Okay, so depending on where that which carbon is attacked, you either have 3-bromo-1-butene or 1-bromo-2-butene. But anyway, this found that at cold temperatures, particularly at around negative 80 degrees Celsius, you produce more 3-bromo-1-butene than 1-bromo-2-butene. But at higher temperatures, especially at around 45 degrees Celsius, you actually produce less 3-bromo-1-butene, and you instead have more 1-bromo-2-butene. So now the formation of 3-bromo-1-butene and 1-bromo-2-butene from 1,3-butadiene and hydrogen bromide actually has two reaction profiles. The one here in blue shows the activation, or the reaction rather, profile for 3-bromo-1-butene, okay? And the reaction for the formation of 1-bromo-2-butene is actually depicted in the graph read. For both cases, the intermediate is actually this carbocation complex with bromine. Okay, so as you can see here, for the second step, so for both cases, the rate determining step is the first reaction, okay, the formation basically of this carbocation. But note that this reaction in blue, which is the formation of 3-bromo-1-butene, actually has a lower activation energy, okay? It has a lower activation energy, and as a result, at low temperatures, then you have enough number of molecules which are actually colliding into each other to form 3-bromo-1-butene. So just remember that from the collision theory, the higher, okay, the higher the temperature is, the higher, okay, the higher the number of effective collisions, molecular collisions, okay, which are basically enough to overcome the activation energy. Now, notice, however, that this product in terms of energy is less stable than 1-bromo-2-butene. But the formation of 1-bromo-2-butene actually has a higher activation energy than 3,1-bromobutene. So you can actually achieve the formation of 1-bromo-2-butene over 3-bromobutene. You can overcome this activation energy barrier by, well, cranking up the temperature and increasing the number of molecular collisions. If this is the case, remember that activation energy is constant at all temperatures. Okay? Now, if this is the case, for the green graph, as we crank up the temperature, you have more molecules colliding in space, which will actually promote this reaction instead, even though it has a higher activation energy barrier. Okay? And then therefore proceed towards the formation of these products, or this product rather, which remember is more thermodynamically stable than 3-bromobutene. That is why, working at a high temperature, you get the product 1-bromo-2-butene, which we will call here as thermodynamic control. And the kinetic control is obtained at lower temperatures just because the activation energy for that reaction is very small.